Let ABCD be a quadrilateral inscribed in a circle with center O, and let E be the intersection of segments AC and BD. Let omega 1 be the circumcircle of ADE, and omega 2 be the circumcircle of BCE. The tangent to omega 1 at A intersects the tangent to omega 2 at C at this point Q. And similarly, the tangent to omega 1 at D intersects the tangent to omega 2 at B at point Q. And our goal is to show that OP equals OQ, that the green segments have equal length. So how do we get started on this problem? Well, it might not be it's a good idea to try blindly angle chasing, so let's try doing this. So we have this point P here, and PA is tangent to the circumcircle of ADE. So let's try doing stuff with that. So we have that directed angle PA, and then we want to PA something where that something is either E or D. And if that something is E, then it just extends to point C, and we can make that nice. So we have directed angle PAC is equal to directed angle PAE is equal to directed angle ADE, which is equal to directed angle ADB. So we have that directed angle PAC is equal to directed angle ADB. And however, directed angle ADB is also equal to directed angle ACB. So PAC is equal to ACB. And that means that the perpendicular bisector passes through this intersection here. So we can go ahead and draw that in. So, and we can also label this point B prime here. And since these two angles are equal, we have that AB prime C is an isosceles trapezoid. So that means that B and B prime are reflections across the perpendicular bisector. And given this, it might help to extend this tangent and make it intersect at a point D prime, such that, and then we get that DD prime is parallel to AC, and therefore this tangent and AD are reflections across this perpendicular bisector as well. And therefore, since we're looking at this reflection intersect this reflection, this point P is just the reflection of the intersection of lines AD and BC. So let me go ahead. They're intersecting on the problem statement. So let's go ahead and make them intersect at a point X. Then P and X are reflections of each other across this perpendicular bisector. And since O lies on the perpendicular bisector, because OA is equal to OC, we discover that OP is equal to OX. And we can do something similar with the point Q. Instead we consider the perpendicular bisector of BD. And repeating our argument here, we discover that this is also equal to OQ. And therefore, the lines OP and OQ are in fact equal to the segment OX. And this concludes our proof. So thank you so much for watching this video. Please subscribe if you'd like to see more.